Ever wonder what's really happening under the hood when you click an icon on your screen? Well, today, we're going to peel back the layers and take a journey deep inside the Windows operating system to see how it all actually works.
So here's how we're going to break this down. We're starting with the apps we all use, and then we're going to follow a single request all the way down the rabbit hole, from the surface level right down to the code that talks to the physical hardware.
All right, first things first, we have to wrap our heads around the single most important concept in all of Windows architecture. It's this fundamental separation of powers between your applications and the operating system itself.
We've all been there, right? An app just freezes up or crashes completely. But have you ever stopped to think why it doesn't just take your entire computer down with it? The answer is an absolutely brilliant architectural choice, a protective wall built around the heart of the OS.
See, this wall creates two totally distinct zones. Your apps, they live in a restricted area called user mode. Each one gets its own little sandbox, its own private memory, and it has almost no ability to touch the hardware directly. But the operating system core, that runs in the super privileged kernel mode, with total, complete control over everything. And that separation, that's the whole reason a buggy app can't just reach over and mess with critical system files and crash the whole machine.
Okay, so let's hop over to the user mode side of that line. If our apps are so locked down and restricted, how do they actually get any real work done? I mean, how does a game render graphics or a browser download a file?
Well, they do it through something called an environment subsystem. The easiest way to think of this is that it provides the unique personality of the OS. It's what exposes all the functions and services, you'll hear them called APIs, that developers use to build their applications in the first place.
So here's how it actually works in practice. An application doesn't just shout directly at the OS core. No way. Instead, when it wants to, say, read a file, it calls a standard well-documented function. That call gets picked up by a subsystem DLL, which is basically just a shared library of code, and it acts like a translator, getting the request ready for one last, very special library called ntdll.dll.
All right, so the application's request has been neatly packaged and translated. It's standing right at the doorstep of the kernel. How in the world does it cross that heavily guarded border from the limited user mode into the all-powerful kernel mode? And this, right here, is the magic trick. It's not a normal function call. To get across that boundary, the code uses a special, hardware-level command that tells the CPU itself, hey, I need to switch modes. The processor literally changes its state, instantly gaining all the privileges it needs to run the trusted kernel code.
And the official gatekeeper, the library that's responsible for making that critical jump, that's our friend ntdll.dll. You can think of ntdll as the bouncer at the club door for kernel mode. It's the final gatekeeper on the user mode side. Its whole job is to take the application's request, trigger that special processor instruction, and formally hand over control to the OS core.
We're in. We've crossed the border. Welcome to kernel mode. Now let's check out the two main components that make up the absolute heart of Windows, the executive and the kernel.
First up, we have the executive. Think of this as the operating system's management team or its cabinet. You've got the process manager, who's in charge of starting and stopping programs, the memory manager, who doles out RAM, the I/O manager, handling all your files. These guys make the big policy decisions. They decide what needs to be done.
But sitting just below the executive is the kernel itself. This is the real engine room. It provides the most fundamental, low-level mechanics for the entire system. Things like deciding exactly which tiny piece of code gets to use the CPU in any given microsecond.
Let's make this super clear. The executive is like the department heads in a government. It decides on policies, like we need to create a new process. The kernel, on the other hand, is the core infrastructure. It's the power grid, the scheduling system. It provides the actual fundamental tools to get that job done on the CPU.
Okay, we're at the final layer. We know how the OS manages itself, but how does it communicate with the thousands of different types of processors, motherboards, and all the other bits of hardware out there in the wild?
I mean, seriously, think about it. This is a huge problem. How do you write one piece of software that can run on an almost endless combination of physical computer parts? Well, the solution is just plain brilliant. It's a component called the Hardware Abstraction Layer, or HAL for short. You can think of it as a universal translator, a single, clever module that sits right between the generic OS and your very specific physical hardware.
And this is the secret sauce for how Windows can run on so many different computers. The HAL is the magic layer that absorbs all those little differences between, say, an Intel processor and an AMD one. It lets the rest of the OS, the executive and the kernel, speak in one generic language, while the HAL does the hard work of translating that into the specific commands your hardware needs to hear.
So let's just quickly retrace our steps on this incredible journey inward. It all started with you running an app in user mode. That app used a subsystem DLL to talk to ntdll.dll, which made the jump into kernel mode. Once inside, the executive decided what to do, the kernel scheduled the work for the CPU, and finally, the HAL translated it all for your physical hardware. It's this beautiful, layered dance that happens for every single thing you do.
You know, this elegant architecture has been the rock-solid foundation of Windows for decades. But that raises a really cool final question. With all our modern technology, what new security features that we hear about all the time are really just a direct evolution of this same core principle? This simple but powerful idea of creating a protected, privileged space for the operating system to live in. Something to think about.
Help me out, please smash that like button, leave a random comment, and subscribe if you want to become a better hacker.